fine.
Yeah. You know what, because we want to save the time, let me start it, okay? Couple of minutes, it was introduction, and then by the time they come here, they hear the main talk. I don't think there's anybody who doesn't know me. Anyway, if you don't, my name is Mohsen Janatpour. I am been here 135 semesters, so been kind of old. But the
Does that
good
include
part of
summer?
it, Nicholas wrote me maybe a month ago, 2 months ago.
Something like that.
Yeah, he wrote me that I defended my PhD. I was your student. As soon as somebody said I was your student, you get excited. And then told me what he was doing. So I called Heidi and said, "Come on, I have a great speaker for you." And there he is. He's going to tell us all about stagnation points, about superfluid, injection to it, and all that good stuff. And I asked him, "Would you like me to give an introduction to the topic?" He said, "No, he's going to cover it all."
Yep.
Go for it.
Thank you.
Give him a hand. Thank you.
My name's Nick. I'm a recently defended PhD student. I'll talk about that in a little bit, but I'm here to present some ongoing work in the field of hypersonics. So I'm an aerospace engineer from school. And so I'll be talking about kind of three main ideas that are big problems in the hypersonics community. The first is stagnation point injection. Second is Mach 10 shock boundary layer interactions. And the third is scramjet combustors. But before we do that, I'm going to give you kind of a background on where I came from. So as Professor Mosen said, about 11, 12 years ago, I was actually a student here at College of San Mateo, taking some math classes, physics classes at Kenyatta and Skyline as well. Eventually, I went to Toronto Metropolitan University to get my bachelor's in aerospace engineering. After that, I went on to do my PhD in aerospace engineering, which I just got from Case Western Reserve University in Cleveland, Ohio. And during this time, I did a couple kind of really cool internships. Actually, while I was at the College of San Mateo, I did an internship at Caltech, where I worked on an experimental problem called supersonic retropropulsion, which I'll talk about in a little bit. I went on to go to NASA Langley during my PhD for about half a year, looking at Mach 10 shock boundary layer interactions, or SBLIs, and scramjet combustors, and some other kind of image analysis, which we'll take a look at a little bit later. And last summer, I was at Lawrence Livermore National Lab, just about an hour away from here, looking at high-speed, high-temperature ejecta, and working on something called light field imaging systems. And I will be starting a job as an experimental physicist there in July. So the way this talk's going to be structured is I'm going to give a really brief intro to hypersonics, just to get everyone kind of on the same page. We'll talk about some really simple concepts like speed of sound, Mach number, shock waves. We'll talk about what changes from subsonic flow to supersonic to hypersonic flow and what that difference means. And then we'll talk about the subject of my PhD research, which is hypersonic stagnation point injection, or SPI. And we'll kind of go through the motivation behind the problem, talk about some historical relevance. We'll go through the experimental design of how we actually kind of look at this problem, and we'll actually look at some results as well. Then we'll look at Mach 10 shock boundary layer interactions, or SBLIs, and we'll end with scramjet combustor experiments at the University of Virginia. So we're going to start kind of basic and talk about kind of just what are sound waves. And so they're longitudinal pressure waves that are caused by oscillations of particles. And I have a little GIF and animation that we'll see in a little bit, but they travel at the speed of sound, which we'll say is A. And A is material specific. So in air, it's about 340 meters per second. In water, about 1,500 meters per second. And in some types of steel, sound travels through that at about 6,000 meters per second. And it depends on the temperature. So for an ideal gas, we can see that the speed of sound is just the square root of the specific heat ratio times an individual gas constant times the temperature. Now, if we've defined the speed of sound, then what we can do is we can define how fast we're moving relative to that speed of sound, which is what we call the Mach number, which is just some velocity divided by that speed of sound. So if you had an aircraft traveling at 343 meters per second in air at STP, standard temperature and pressure, you would be moving at Mach 1. Now, here's a little GIF that kind of shows you how these kind of pressure waves can move through the air, kind of see these collisions and oscillations of particles, and where the air kind of bunches up and that oscillation travels, you have an area of kind of higher pressure, and behind it, where they're spreading out, it's called rarefaction, you have an area of a little bit lower pressure, and this is how the sound from my throat is reaching your ears in this room right now. Now, if we were to plot kind of a bunch of Mach numbers on like a number line starting at 0, we would start in this region called subsonic, which is between the Mach numbers of 0 and 1. And here there's some kind of interesting places between 0 and 0.3. We call this the incompressible zone, where you can use things like Bernoulli's equation, which you might learn about in a physics class here or later if you go to university. And from 0.3 to 1, you can't really use Bernoulli anymore. It's not very good. It's not going to work ever again, actually, past 0.3 without some real corrections or just completely different sets of equations. And that's because the flow starts to become compressible. Now, between 1 and 5, this is what we call the supersonic regime. And so now we're traveling faster than the speed of sound. And there's a set of equations you would use called the isentropic flow equations. Right around Mach 1, you have what's called the transonic regime, which is between 0.8 and 1.2. So you're kind of just below the speed of sound and just above it. And this is a really complex regime where there's a lot of research focused on here. And it's very difficult and not something that I do. I kind of focus on the hypersonic regime, which is Mach 5 to Mach 10. And I'll talk a little bit about kind of why we delineate supersonic to hypersonic, to high hypersonic, which goes up to Mach 25, to reentry speeds, which are even above that. And really what you get into here is that you start moving so fast that you primarily are dealing with extremely high temperatures. As we'll see later, the temperatures near the leading edges of vehicles can be in excess of 10,000 Kelvin, which is about twice the temperature of the surface of the sun. And far beyond the melting point of any materials we have today. So that's a real problem if we want to start flying at those speeds. And you deal with ionized air and turning the air just directly into plasma. You start hitting molecules in the air so hard with so much energy that the H2O, CO2, N2O2, just all these different gas species are actually splitting into their constituent atoms, and you have all of these different species of gases around your vehicle that are wanting to recombine immediately. So there's all this chemistry happening around your vehicle. And so it's a very complex, difficult problem when you get kind of past Mach 5. But the biggest one is really these really high temperatures. That's kind of what we're going to be focused on mostly for this talk, because the other stuff is very complicated. And one kind of important note about supersonic flows, kind of just and hypersonic and so on, as it pertains to the difference from subsonic flows, is that information only travels in one direction in this type of flow. And so I'm going to talk about that right now. Like, what do I mean by information only travels downstream? And so you can actually, you've probably seen this in videos. You actually see it every day as planes fly by. But in subsonic, you can imagine that, and you can see it when you look in the sky, is that when an airplane is passing by or even coming towards you, you can hear it before it's actually reached you, right? And so the sound that it's emitting is traveling faster than the plane is traveling, right? And that's why the sound of it reaches you before the plane actually reaches you. Now, if you start to accelerate kind of close to Mach 1, then those pressure disturbances are going to kind of bunch up, because now the sound of the airplane is traveling at the same speed of the airplane, and it's not going to get to you until the plane gets to you, right? And so when you start going supersonic, you get this kind of cone of influence where now the sound that this plane is emitting, you actually need to the plane is going to pass you before you actually hear it. And so you can see videos of this actually, where I should have put one in the talk, where you can see kind of fighter jets flying by out at sea, and you see it coming, and it passes you, and then you hear it. And so that's kind of what I mean by information only traveling downstream, is that the flow didn't really know that this airplane was there until it got to that point in the flow. There's no information about this airplane kind of in front of these two angles right here, which are shock waves. And so we'll give a really brief introduction about shock waves, kind of what are they? There are these discontinuous changes in the flow in pressure, velocity, temperature, density, and something called entropy. And it's a place where continuum mechanics don't really break down. And so when you start solving these kind of compressible flow gas dynamics problems, you'll have your set of equations that work all the way until you get to the shock. And then you can't actually solve what's happening in the shock. You have to use a set of equations that jumps you across it, and then you keep going. If you want to know what's happening inside of a shock wave, you have to do something called statistical thermodynamics, and it's a lot more complicated and kind of a higher level grad class. And they're really thin. So they're on the order of hundreds of nanometers, which is on the order of wavelengths of light. It's about 3 orders of magnitude thinner than the diameter of one of your hairs. So these are really, really thin, and they're not isentropic, which means you kind of can't go back. So what I mean by that is you kind of incur permanent losses to the amount of energy you have available in the flow. And so when you want to put this through an engine, for example, when you go through a shock wave, you're losing kind of how efficient this engine can be. And just to give you an example, so we have just a little schematic of like a normal shock. So imagine you have a Mach 5 flow and it hits a shock wave. You know, how much are these kind of parameters going to change as you kind of just go across the shock? So over this extremely thin piece, about 100 nanometers, your Mach number is going to go from 5 to 0.4. Your pressure is going to jump by a factor of almost 30, your temperature by a factor of almost 6, and your density by a factor of about 5. That's over about 100 nanometer, 1,000 times thinner than the diameter of your hair kind of region. So I'm going to start talking about my PhD research, which is stagnation point injection. And stagnation point, basically, for all intents and purposes, basically just meaning kind of the front and center of a vehicle. It's kind of where the flow comes to a stop and then has to reaccelerate around the vehicle. So I showed this image earlier and I called it supersonic retropropulsion. And that's because the entry, descent, and landing, or EDL community, calls it supersonic retropropulsion, or SRP. And the reason that this is kind of a configuration of interest is, currently the highest mass payload of anything we've landed on Mars so far is about 2 metric tons. And in the future, we'd like to land humans. But those payload requirements are estimated to be on the excess of 100 tons, and current EDL technologies are just not feasible. We've actually kind of already reached our limit as to what's landable on Mars using kind of the parachutes, the sky cranes, the bouncy ball, if you're familiar with any of those technologies. And so the idea behind supersonic retropropulsion, or SPI, is you would have this little lander that would, presumably be carrying life support systems, astronauts, and you would be adding rockets basically to the front of it so that you would be slowing down with the kind of summation of your drag plus the thrust that is being produced by these rockets. So you can imagine, instead of that kind of Apollo capsule, the lander with the big blunt front, you now have rockets on the front of that are shooting forward to try to push you backwards and help you slow down. And we actually see supersonic retropropulsion pretty regularly on the Falcon 9 rockets. And so these are kind of 2 videos. On the left, it's infrared. On the right, it's just like a phone video that someone took. And you can see this giant plume igniting here. And they even call it Mars Relevant Retropropulsion Regime because this is kind of the identified enabling technology by NASA for landing on Mars. So I'll let that play again, actually. Let's go back, forward. And so you can see that just this tiny little dot in there is the actual Falcon 9. This is a huge bow shock where you can see the pressure jump increase basically instantly. It lights all of its rockets, and there's just this huge plume, a bunch of unsteadiness. And that's kind of what brings us to the problem behind stagnation point injection, is that we don't really know what's happening in front of the rockets. The fluid mechanics are really complicated. They're difficult to model. And there's really just no answers out there. So this is a picture of one of the models that I used in the Purdue Boeing AFOSR Mach 6 quiet tunnel in Lafayette, Indiana. And so it's a aluminum cone with a little jet right there in the front. So the diameter of this kind of spherical nose is about 3/4 of an inch. We have some instrumentation in the back. This thing that's attached to it is called the sting. It's what holds it in the tunnel. And the primary diagnostic that we use is an imaging technique called schlieren imaging. And all you need to know about this is that we're just shining collimated light right where we want to kind of view the flow field. So we want to see these flow dynamics. We shine collimated light through there. That light will refract with density changes, and we just capture that on a high-speed camera. And so we're able to take high-speed video that lets us view this flow field and then kind of interpret the motions. We can now use math to kind of figure out what's happening. And so this is a picture from one of my experiments. We're going to be looking at videos later, but I wanted to show this so we could all get on the same page with some of the terminology. And so this is the kind of tip of the model right there. You can see that orifice right there is actually firing out a Mach 1 jet into a Mach 6 free stream. And so from left to right is the tunnel flow, which is moving at Mach 6. And then out of this little jet, we are injecting some gas at about Mach 1. And you'll see a whole bunch of features in this image. And so to start kind of defining those, we'll start with these shear layers, which are coming off of the edges of the jet. We have the triple point, which connects the shear layer to the Mach disk, which is where the jet flow shocks down into a subsonic flow. So in this region right here, right outside of the jet, it's actually supersonic because it's expanding. We have the contact surface, which is this kind of line that's in between the bow shock and the Mach disk, which is where the jet flow and the free stream flow or the tunnel flow first interact. And so you can see that kind of density change. Remember, what we're looking at in this kind of image are changes in density. So this contact surface is where this free stream Mach 6 flow and this Mach 1 flow from the jet are first touching each other. And as I had said earlier, leading edge temperatures in hypersonic vehicles can be in excess of 10,000 Kelvin, which is about twice the sun's surface temperature. And so, just go back. And so we need some other way to cool these vehicles because the materials that we currently have today, this is way beyond their melting point. So if we fly something and we experience these temperatures, it's going to be destroyed. We need something else to kind of aid us to get to these speeds. And so the idea is that by injecting some flow at the front, we'd be able to kind of lower the heat flux onto the vehicle, provide some sort of cushion onto the vehicle, and we would experience lower temperatures. And kind of historically, the way that experiments have been run is they vary something called the aerodynamic thrust coefficient, which is found as this universal governing parameter for the dynamics associated with all of these kind of features, which is just the thrust divided by the free stream properties or kind of like the atmospheric properties. You can think of as that. And so what we're going to do is we're going to kind of look at some videos of this. And what we're going to be doing is varying this parameter, the thrust coefficient. And the way that we're going to be doing that is by varying the thrust of the jet. And so we do that by changing the pressure of the jet, which is, back here, supplied by a cylinder. It'll always stay at Mach 1. That's just a feature of kind of sonic and supersonic flows. So no matter how much you increase the pressure, it's always going to stay Mach 1 because it is a geometric limitation. So we're going to start by looking at this low thrust coefficient videos. And so these are taken at 76,000 images a second, so very high speed cameras. When we run the tunnel only experiences hypersonic flow for about 3 seconds. And that's actually a pretty long time for a hypersonic tunnel. The one that I worked at Caltech was about 1 second. And the other tunnel in the room just adjacent to me at Caltech, the total test time was about 30 milliseconds. So we're using very, very high speed cameras, we're using lasers, all sorts of stuff to try to capture these images. But, and then the quiet and noisy, the tunnel that I'm working at, or did work at, has a kind of special feature where it can run in what's called quiet flow, which essentially means there's no turbulence in the free stream. It's the only hypersonic tunnel in the world that can do that, but I won't really be talking about that today. I'll just be showing videos. So while we're looking at this video, we can see that there's these big vibrations and oscillations and these kind of features. We can see that the triple point kind of looks like it's moving forward and backwards. We can see that there's like this bump that kind of appears every time it moves forwards and it travels along the bow shock. And we'd like to be able to kind of pull out these motions and isolate them and maybe look at their energy content as we change the thrust coefficient. Because as we continue to increase the thrust coefficient, you'll see that the flow becomes a lot more steady. And so this is kind of a problem if we were to experience it in flight, but steady flow, this is nice. We can design for this because our parameters aren't changing. The temperature behind the shock, the pressure behind the shock, they aren't changing because the shock is nice and steady. With all of these fluctuations, all of those parameters are changing constantly, and your vehicle is going to experience these kind of dynamic loads, which are really difficult. And at the end of the day, this is changing the force on the vehicle, and so your astronauts are going to get a real bumpy ride if they're running in that. So you can see at low thrust coefficient, we have this kind of unsteady motion. At high thrust coefficient, we go to this steady motion. So what kind of techniques do we use to kind of pull out different motions and track the energy as we increase the thrust coefficient? In my research, I use linear algebra techniques. So this one is going to be called the proper orthogonal decomposition, or POD. And basically what this shows is it's kind of like a phase diagram. And so basically areas of red are correlated to each other, and areas of blue are correlated to each other. And then areas of red are anti-correlated to areas of blue. And so the way that you would interpret this is that you can imagine this little red region right here, the shock is moving forward. And at that same time, the blue region is moving backward. And so that is showing you that kind of bump that was traveling along the shock. And then this little region right here with the triple point is kind of that flapping forward and backwards. So as the triple point moves back, it's leaving behind this little area of blue. As it moves forward, it's leaving behind this little area of red. And that's how we interpret oscillations. It's a really popular imaging technique in hypersonics. And what's really nice about it is that it tells you how strong this mode shape is. So we call these shapes modes, and there's a lot of them. I'm just showing one right here. But you can see in the low thrust coefficient, so at the top here, I have low thrust coefficient, and we're increasing as we go down. In the low thrust coefficient data, I have this 23.5% energy, so we have pretty high energy. And as we increase the thrust coefficient, and the flow becomes a little bit more steady, it's decreasing in energy. And so this technique allows us to kind of pull out this one motion, look at its energy, and it matches what we see in the video. Now, at the same time, though, we were kind of seeing the flow become more steady. And so we're also able to pull out different shapes, such as the longitudinal mode, which you can see is just kind of that forward and backward breathing motion, which as we increase in thrust coefficient, increases in energy, which is kind of exactly what we saw in the schlieren. Now, one thing that we can't do with this technique, and you kind of see this in the frequency spectra, so this is just kind of showing you what kind of frequencies this mode is really capturing. And so if you were to ask me, okay, well, what frequency does this show from the POD? I wouldn't really be able to tell you because you have all these peaks all over the place. You don't really know. But we use another technique called the dynamic mode decomposition, which is another linear algebra technique. And this can pull out these individual modes. And so you can see this shape before, and maybe it's a little easier to understand what's happening here. So you can see this kind of forward fluctuation kind of turn into a perturbation that travels downstream and perturbs the shock right here. And it pulls out modes at discrete frequencies. So now I can say, well, I know that that mode that I was looking at with that flapping and kind of the triple point is happening about 27 kilohertz. I know that that longitudinal kind of breathing motion that's really stable happens at 200 hertz. And I know that this kind of vortex shedding feature that's coming off of the triple points is happening at like 31 kilohertz. Some other measurements that we do is we like to measure kind of how far the shock stands off from the jet. And so as part of my experiments, I inject a bunch of different gases into the free stream. So we inject argon, CO2, helium, sulfur hexafluoride, which is SF6, and air. And so you can see that depending on the gas that we inject, we get different standoff distances. And even something simple like this has just never been done before. People have really just injected air or nitrogen. And then another thing we look at is we can correlate kind of the frequencies that we see. So we're measuring the pressure in the jet in the chamber of the jet, so kind of where the jet flow is being supplied from. And we can find that peaks in kind of the spectra. So this is just kind of like a Fourier transform of the pressure measurements, match kind of these different flow features that we're seeing in both the DMD, the POD, and something called the SPOD, which is, for all intents and purposes, basically the same as a POD. It's just happening at a single frequency. And then just to show real quick kind of the difference in injected gas. So this is injection of sulfur hexafluoride, or SF6. And you can see these really big Kelvin-Helmholtz instability waves forming here. And so, for example, something like this had just never been seen before in this flow. And actually, you guys in the room here are probably one of maybe a handful of people who actually even know that this exists in this type of flow, because we haven't published it yet. And so, yeah, so to move on, I'm going to start talking about what a Mach 10 shock boundary layer interaction is, or an SBLI. And I will start by kind of showing the schematic. So basically what happens is you have something which is called a boundary layer, which anytime anything's moving through any type of fluid, gas, liquid, it's going to develop this thin layer of fluid that's kind of sticking to the surface. And the velocity is actually zero at the surface. Even if you're moving at Mach 5 through gas, the velocity of the gas at the surface is zero. And then it increases to whatever the actual speed is by the time some distance away. These are really, really thin layers. And all the heating and drag is occurs on the vehicle is basically responsible from these boundary layers. Now, there's something that happens anytime the flow needs to change direction and going up a ramp like this. And so you can imagine that, you have all these different shapes going around, like space shuttles, going around vehicles, fighter jets, right? They're not just a tube, they have angles. Any one of those angles, when you're flying supersonic, is going to generate a shock. And that shock is going to interact with that boundary layer. And now I said the drag and the heating come from kind of what's happening in the boundary layer. And so if you have a shock interacting with it, you're going to get increased viscous heating, you're going to get increased drag potentially. A lot of things can happen. And this shock is actually moving forward and backwards. And so while here I'm showing a turbulent boundary layer, you can definitely have a laminar boundary layer. Actually, boundary layers generally start like that. And what that means is basically the flow inside the boundary layer is all kind of moving nice and orderly in kind of the same direction all the time. If you were to drop like a little marble in there, and then you were to drop another one in the same place, it would always follow the same path in a laminar flow. In a transition region or a turbulent kind of flow, you drop that marble in at the exact same place, and it's going to go in random directions every time. You really can't predict what's going to happen. And in these turbulent layers, you get really high heating because there's so much mixing between the particles. And so where might you see a shock boundary layer interaction? Well, basically what I said is anytime you have some kind of geometrical change that's coming out into the flow, you're going to have a shock in supersonic flow. So anytime you have this kind of change, there's a shock there, and that shock is interacting with that boundary layer, which is responsible for the heating and the drag. And you need to know what's going on. So remember, around these shocks, you have these abrupt changes in flow properties. The temperature is kind of the one that we really care about. And the separation shock is oscillating back and forth. And so when it's moving forward, it's seeing kind of like higher velocity. And it's when it's moving backward, it's kind of seeing a little bit of a lower velocity. And so these properties behind it are changing very rapidly. And this separation shock can actually instantly transition the flow from laminar to turbulent without actually going through any sort of transition region. And so to give some kind of historical relevance about this, there was a test vehicle called the X-15, which on one of its tests was carrying this kind of scramjet dummy engine. They wanted to know about just running engines in supersonic flows. And so this was flying at Mach 6.7. And basically what happened is there was a shock boundary layer interaction. We didn't really understand them too well at this time. And basically you can see right here, kind of right where that shock was interacting with the boundary layer, the temperatures became so high that it just melted through this kind of support pylon that was installed to carry this engine, and the engine just kind of fell off mid-flight. So these are really important things for us to know about because we want to be able to fly at these speeds. And so NASA has a Mach 10, 31-inch Mach 10 tunnel. And so what they did was they installed basically different shapes in the tunnel to kind of generate these shock boundary layer interactions and take video, just like we saw before, the same schlieren images of them. And so here you can see a high-speed camera attached to a bunch of polarizing kind of equipment. So this is a specific imaging technique called self-aligned focusing schlieren. So it basically works the same way, where it's just going to pass light through what you're trying to look at, and it's going to refract, and you're going to capture that back onto a camera. This is Josh Weisberger. He's a friend of mine. He's an experimental researcher there. Really good guy. So he's running a whole bunch of what's called the DAC, the data acquisition system. And this is this kind of vertically mounted imaging system. And then down here is the tunnel. And so you can see it here just kind of from another view. And so I showed this diagram earlier, and so I'm going to be showing a couple videos now. And the region that we're going to be looking at is kind of this little highlighted region here, right in front of whatever kind of shape change we're putting in. We're going to put in a couple different ones, and we're just going to be looking at what's happening. And so to start, we're just going to have a flat plate. And so we're going to compare it to kind of the baseline run. So on the left here, you have a flat plate with what's called no trips. And so basically this would be kind of, you call this laminar flow ahead of the shock. And then we have what's here is called pizza box trips. It's basically just a bunch of little perturbations kind of ahead of it, little like, you can think of putting like corrugated piece, something there just to like mess up the flow. Sandpaper would do it. And what that does is it kind of instantly trips the flow from laminar to turbulent. And so you can kind of see it a little bit in the schlieren, where this is maybe a little bit wider. There's a little bit more mixing happening, where this looks a little bit neater. But you can definitely see it in the dynamic mode decomposition, where we're trying to pull out some of the features that are happening here. If you look closely, you can kind of see that it's kind of wobbling up and down. But when you perform kind of one of these linear algebra techniques, you see this kind of nice vortex shedding feature that's happening right around 30 kilohertz. And in the tripped flow, which is kind of chaotic and mixing a lot, you can see that it's kind of mixing together a little bit. It doesn't have these kind of nice, sharp delineated regions. So then what we did is they put a 30-degree ramp as that kind of obstacle where you're going to start generating the shock. And so on the left here, you can see in the laminar flow where there's no pizza box trips, you can see kind of this nice stable shock here. You can see kind of that same flapping feature. And in the turbulent flow, you kind of really can't see the shock. And this is just kind of oscillating a little bit more. And so that's really obvious when we look at the dynamic mode decomposition, where you see the same vortex shedding feature. But now you can see kind of these other regions. And what these are is, if you look closely, you can see kind of these little lines that are appearing that connect this kind of sonic line to the shock. And what the DMD is telling you is basically that for every vortex that's being shed here, it's actually correlated to some perturbation in the shock. So that's how we kind of interpret these videos and images from the DMD. And again, looking at kind of the turbulent flow, you can see that there's just a lot more mixing. And now that these vortex features are not correlated to the shocks anymore. Finally, they put a kind of large cylinder. Actually don't know anything about how large that is. It's kind of a vague term, but that's what they named it. They put a large cylinder as the obstruction. And so you can kind of see this similar behavior as the 30-degree ramp. And you can see this kind of what's called a shock foot forming right here. And when you look at the DMD, you kind of see the same thing where these vortices are correlated to different features kind of higher in the field of view. Now, at the time of these experiments, they weren't really sure how big this shock would be, so they kind of missed a lot of it. It's out of the field of view, so they're going to be running new experiments with a little bit more information that's actually informed by the analysis that I did, where they're going to be looking kind of further upstream, so over here to the left, and further just kind of vertically up to try to correlate as many features as they can about what's happening. And remember, the reason why we're looking at things like these is because we want to know what frequency things are happening in the flow, because the properties like temperature and pressure are changing relatively close to these frequencies is the idea, right? If the shock is moving at 20 kilohertz and vibrating, then the temperature is also going to be changing kind of at that same frequency. And so now I'm actually going to start talking about the scramjet combustors experiments. And so I'll start with kind of just like a really brief talk about jet propulsion, specifically ramjets and scramjets, and kind of what's the difference, why do we use them. And the idea is, I talked earlier about shocks and how you kind of incur permanent losses. And so when you go through a shock, you lose pressure that you can't recover. And that pressure is something that you would have used to turn into thrust. Is kind of the idea behind engines. And so in a ramjet engine, you have supersonic flow coming into the engine. You use compression shocks to decelerate the flow to subsonic. Then you ignite, you inject fuel, ignite it, and you expand it out the back, and it's supersonic on the way out. And that's how you generate thrust. Now with a scramjet engine, which is an experimental concept, we don't have vehicles that use these. The flow is always supersonic. So now you are still decelerating the flow a little bit, but you're keeping it supersonic, trying to not incur those kind of permanent losses so much. And so this is very difficult because now you're trying to inject fuel, you're trying to light a flame in a supersonic flow. So you're traveling thousands of miles an hour, and you're trying to light a flame, keep a candle lit, essentially. And so why do we need a scramjet versus a ramjet? Basically, this compression shock to subsonic, the losses from it just become so great that this engine basically completely loses all efficiency really past Mach 5. And so if we want to fly faster and faster, we really need scramjets. You might have heard of the concept of an SSTO, a single stage to orbit vehicle, which is something that can take off on the ground, go all the way to space, and come back without any rockets dropping off, like the space shuttle or the Falcon 9s or anything like that. If such a vehicle would ever exist, it will use a scramjet engine. So one place that you might have seen ramjet engines is with the SR-71. The Blackbird has two J58 ramjet engines on the back. If you know anything about it, then you'll know that these little nose cones actually move forward and backwards depending on how fast the plane is flying, because it's trying to catch where that shock is right perfectly, so to minimize those pressure losses. And it flew about Mach 3.2. For scramjet aircraft, which are experimental, you can see just a couple mock-ups here. This is kind of like the SR-72 from Lockheed Martin. This is, these are just renders, so they're not real aircraft. This is kind of a NASA Wave Rider. And then if you've watched any movies recently, you'll know that Tom Cruise actually flew one of these at Mach 10 in the movie. And kind of a interesting story about this is they built a really detailed life-size model of this plane and kept it at one of Lockheed Martin's hangars. And so Chinese satellites actually saw it and thought it was a demonstrator aircraft for a hypersonic vehicle, and actually directed other spy satellites to take more images before realizing it was a movie prop. So it's kind of funny. So at the University of Virginia, there is a scramjet combustor experimental section, which is actually vertical right here. And again, they're using this kind of SAF system, which is just a schlieren system essentially, with a bunch of polarizing optics and a really high-speed camera. It takes about 110,000 images every second. And the way that, so this is vertically oriented, so the top is actually right here and the bottom is over here, is that you have a Mach 2 nozzle. And then what I'm going to be showing is video and analysis from 3 different parts of this combustor section. So we're going to be looking at where the fuel is being injected. We're going to be looking just downstream where there's this kind of cliff inside of the combustor. And we're going to be looking at this kind of little ramp section. We want to learn about how the flow acts as it goes from this kind of first to second to third view. And so these are just kind of still images to kind of give you another idea. So this is kind of fuel being injected into the scramjet engine. Remember, the flow is actually moving twice the speed of sound coming into here. So we're injecting fuel, igniting it, and expanding it out the back. This is kind of that middle view, so this green right here, and then in the back you have this ramp. And even just from the still images, you can kind of see that there are these wave-like features here. This is kind of them stitched together. And so we'd like to know, what are these waves? Where are they coming from? What's generating them? What frequencies do they exist at? We want to know all of this information so that we can learn more about how the scramjet engine is actually working. And so here are some kind of the raw video. So this is taken at 110,000 images per second. And I have kind of the schematic just up here again, so you can see that this is kind of the fuel injection. This is a little bit downstream of it, kind of on the bottom of this little cliff. And then there's some ramp that's a little bit downstream there. They're not necessarily synced up or anything, so you can't like directly say every time something happens here, you see it here and here. It's just kind of independent videos of each of these locations. But we can use the dynamic mode decomposition to try to pull out kind of interesting features. And so to kind of give you an idea of what I see when I look at this, I'll kind of tell you about some of the analysis that I did on the scramjet, which are these videos that we published recently. Has kind of informed a next set of experiments with NASA and the University of Virginia, because we kind of found some things that were pretty interesting. And so the first was, it's not shown here, is that there are these fluctuations in the injection system. Pressure is changing a little bit, so sometimes a little bit more fuel comes out, sometimes a little bit less fuel comes out. And that's normal. Every system has a slight imperfection. And so what that's showing in the DMD is that basically it's fluctuating back and forward, backwards and forward. So first there's a fluctuation on the bottom, and then there's one on the top. So that's coming from the fuel injection line. Now, with every one of those kind of injection oscillations, is what you have is this shock right here also is oscillating. So because the fuel, sometimes a little bit more, sometimes a little bit less, that's causing the shock to move a little bit further away when there's a little bit more fuel, a little bit closer when there's a little bit less fuel. It's kind of pushing it forward and backwards. Now, every time there's an oscillation in the shock, all of the post-shock parameters change, right? We saw that earlier where basically the shock, your pressure, temperature, density, everything changes after you move past the shock. So if it's oscillating, everything after it's oscillating too. Every time there's an oscillation here, what you have is this little expansion that's changing around this cliff. And so this is actually changing to a different Mach number every time it moves around this little geometric feature. And then with every oscillation there's a set of waves, which are just basically areas of different temperature, density, etc., that are kind of impinging on the surface of the scramjet. So now, from a design perspective, why do we care about that? The reason why we care about that is that these are going to manifest as vibrations in your engine. And if you aren't considering these kind of vibrations in your design, you're going to vibrate a lot, and maybe your vehicle just falls apart. And I don't have a video of it here, but if you've heard of the Tacoma Narrows Bridge, it is a bridge that was built, I think, up in like the Seattle area. I'm not sure. But basically, this was kind of before we kind of knew about like harmonics. Maybe you've heard of an opera singer singing and hitting the right note and breaking a wine glass. It's the same thing that can happen in a scramjet, is that if this frequency hits the right frequency, your scramjet can just break, But basically with this bridge is there was gusting air, and it was just gusting at the right frequency where this bridge basically started experiencing these huge vibrations and just completely collapsed. And so this is a real design consideration in all of engineering. So it's really important. And that's kind of the end of my talk. So I hope you enjoyed it. I just wanted to kind of show you guys some open problems in hypersonics, stuff that I've worked on. And, like I said, I used to be a student here, like many of you, about 11 years ago. So I hope you thought it was cool.
Now, before do some questions, I have captive audience. I want to tell you announcement. This Friday at 7:30 in the planetarium, we are giving a scholarship to award, actually, Michael Chris Award to 2 students. This started after you left. So papers are good. They get award, and this year we have 2 young ladies, charming. They have written excellent paper. If you're interested in this kind of stuff, in particular, the papers are about a little bit different, jumbo and Jim Webb telescopes, things like that. This Friday at 7:30 in the planetarium. Fair enough? Okay. Now, I have one quick question that I couldn't get it. Is when you go from laminar to the turbulent flow around the boundary,
Yeah.
how much is the thickness of the boundary layer?
It depends on the length. So when the boundary layer, so for example, if there was flow coming in and hitting this table, the boundary layer would be infinitely thin at the tip. And then as you kind of just proceed downstream, it just grows.
Yeah.
So it depends on how long it gets. So it depends. I'll say the boundary layer on like a truck, like a supermarket truck, carrying a bunch of like a big rig. At the very back of the top of the big rig, I think is on the order of like a centimeter.
Okay. Now, at the
Something like
stagnation points, if you're creating sometimes turbulence.
Yeah,
right?
so the stagnation point, so if you have like a vehicle like this, and you have a free stream, if you were to kind of draw the way that the flow would be going, it'll hit some point right here where it actually comes to rest, and then has to change direction around this. And so this would be different than flow that kind of naturally moves around it. Right on the center line, it comes to this point where it actually stagnates. So the velocity is actually 0 right here along the center line of whatever this vehicle is. So that would be what the stagnation point is generally. And so on an aircraft, on a wing, you have some shape like that. And if it's at some angle of attack, then one of the theories behind why it generates lift is basically instead of the stagnation point being right down in the center, you're actually moving it down here. And so the pressure is actually higher here because you've changed velocity into pressure, essentially. You've kind of regained some of your pressure. And so you have an area of higher pressure down here, lower pressure here, and so you generate lift. So that's kind of a real basic way of how a wing works too.
But also that affects tremendously the temperature, correct?
Yeah, so all the properties are all changing. Yeah.
Any question, anybody? No? Yes.
I do have one from Zoom. So Claire states, I joined a little late. I'm interested in where Mejia works today.
Yeah, so I'll be starting as an experimental physicist at Lawrence Livermore National Lab in July. So I'll be about an hour away.
I have another question.
Yeah.
What took you to Ohio?
So the student that I was doing the internship at Caltech under became a professor in Ohio and then invited me to be his first PhD student. And it was to continue the work that we did during the internship, but as a PhD. So it was with a problem that I already liked, with someone I already knew, so it was like obvious.
Super.
Yeah.
Anything else?
I guess I'll ask one. As a CSM alumni, right? who's now built a successful career in STEM, right? What helped you stay focused and grounded while you were a student here pursuing your degree, taking into consideration that most of you students right here are in the STEM field?
Yeah, that's a good question. So I think at the time, what I was really excited about was actually like SpaceX. I thought it was really cool, back then around 2014, 2015, these kind of boosters coming down, and I wanted to be a part of kind of the, I think my lifetime, I was born a little bit too early to kind of travel through space. But I thought it'd be really cool if I could leave behind something that would enable like future generations. And so that's what I really wanted to do. And I worked hard here, went to Mosen's physics classes, did well, went to university and, ended up being kind of exactly where I wanted to be, which was kind of working on, enabling technologies for Mars landings. It's not what I'll be doing at Livermore, but, it's all related, right? It's all science.
It's always cool to see students succeed, right?
Yeah.
Do you work with or did you look into the floor on the shuttle tiles?
No, yeah. So the tiles, that's a totally different technology. That's like a ablation based,
Right,
yeah.
it is.
So one of the things that I had said was that, we have these really high temperatures. And so it's far beyond the melting point of any materials. And so one of the ways that we get around that is just by sacrificing material. So on the front of kind of our space capsules, we have these ablation shields. And they're basically meant to get really, really hot and then kind of crumble away and take the heat with them. And so that's one design that we use. Now the space shuttle was a little bit different than that, in that it had these, amazing ceramic tiles that could get cool. They could cool off really fast, and the space shuttle was designed to come in at a certain angle, which kind of limited those kind of high temperature shocks effects. So there was a lot going on with it. But yeah.
Anything else?
I have another Zoom question right here from Joseph. What was your favorite class you took at TSM and why?
Mine.
Yeah, I still remember a question you asked in optics about looking at a fish and trying to figure out where it was, and I didn't get that question right on the exam. But I think I really liked. It's tough. I mean, I think the physics classes were really fun, but I also had a really great math professor at Kenyatta College who's since retired. His name was Po Tong.
Yeah.
But it's all about what you put into them. So like in the math classes, sometimes I would stay after and talk about different subjects. There's a professor, I think he's still here, Yuri Sushko, who I used to talk with after classes. So, if you're interested in things, I think your professors will find that they'll be happy to talk to you about it. But if I had to pick, maybe the physics classes, because you get to do some experiments.
Yeah.
And I'm an experimentalist, so.
There you go.
Yeah.
Take our classes.
Yeah.
One quick question. So as an experimental physicist, will your job be similar to what you're doing, what you would describe, or
It's a
something
little
different?
bit, it's different. So at Livermore, I'm going to be looking at really, really tiny particles that are moving really fast. So actually a lot faster than this. Think of particles that are the 10 micron, 50 micron. So smaller than the diameter of a human hair, but moving at 14,000 miles an hour, really high temperature, and basically looking at imaging techniques that you can use to kind of get 3D fields and look at them and how they're evolving in flight. And also looking at ways to generate these ejecta. And so there's a particular instability called Rickmeyer-Meshkov instability, which basically, if you have a material, actually just draw a picture again. So what we'll be doing is we'll have this little target right here, and we're going to hit it with a very powerful laser on this side, and it's going to cause this side to ablate. So this is one material, this is the second material. This material is just going to break off and kind of like really fast, instantly. When that happens, a shock wave is actually going to travel this way and then hit this surface and reflect back. And when that reflection occurs, little particles are going to be ejected from any grooves or defects. So you can actually, if you engineer the material to kind of look like this, right here, you're going to get jetting of materials at really high velocities, really high temperatures. And so we'll be kind of doing this at some laser facilities, at the gas gun facilities, and trying to image the particles that are coming out the other side. And that has applications for kind of national defense and national security, but also energy with the fusion research that's ongoing at Livermore.
Oh, actually, that brings in, I don't know how much has changed. Years ago, I was working on the tires for the shuttle, and I was working on the tooling end of the game. Question, I don't know how much has changed now. I'm talking about back in the early 70s and so on. Who does your toolings now? Or do you guys,
I have no idea.
no idea?
Yeah, the machining, you mean?
Yeah, because
So we have it's all in-house.
Yeah.
So we can't, it's controlled information.
at that time, NASA put the bid to two companies, Fisher and Coors.
Oh, yeah.
Yeah, and I was working with Coors and we lost the contract, didn't get it. And the reason was that the tolerance that they wanted was too expensive for us to do.
Yeah.
Raise my curiosity, who does, because this takes amazing
So
tooling.
these are made in-house.
Oh, wow.
Yeah. So we have our own engineering division, that's
Wow.
material science and, manufacturing, and so they'll
Yeah.
make those.
This is amazing, by those of you who are there. Amazing tooling takes to make that,
Yeah.
really is.
It's, way beyond, I don't know how to do it. Yeah.
I-
So it's not my job.
Any question?
I have another question from Zoom. Nermi, he's asking, they're asking, this is known as one of the hardest majors to pursue. Did you ever second guess your path? What motivated you to continue?
I never second guessed my path. And about the motivation was kind of what I talked about earlier, which was just I wanted to be part of kind of eventual space flight and space technologies. I had done an internship, so I think being involved and so while I was at CSM, I did an internship at Caltech in hypersonics. In my undergrad, I worked in a lab that was at the school, which was not in hypersonics, but it was still a lab just to be involved in. And then so that's how I stayed motivated, was kind of by not just doing schoolwork, but by also doing what I wanted to do, but just at the level that I could do it then, which was kind of as an assistant or whatever. You get to be there and you get to see the experiments, even though you're not necessarily running them.
Can I add one thing to this? If I recall correctly, he was around 25 years old when he was in my class. Am I correct? Somewhere in that neighborhood?
I don't know how.
Yeah.
Now. Oh, me.
You?
Yeah. Okay.
Yeah.
Yeah.
Oh, no, I was lower.
I was like,
It was
I don't know
around
about that.
25. The reason
Yeah.
that I'm saying that, I noticed that the student like him, the key to it was that they were serious about what they wanted to do. Am I correct? And that is really key to it. To you guys, if you want to do something, if you're grabbing, you have to be serious about it. That's the bottom.
Yeah, it's true.
Any other question?
And I'll
Yes.
say, so I got a piece of advice from my mentor at Caltech when I wanted to be involved, but I was unsure, like, I don't really have the skills, I don't know anything about flow, like how could I work in a flow lab? And he told me just to not take no for an answer from a professor specifically. And he basically said that when he wanted to work in the hypersonics lab at Caltech, he went to the professor, Dr. Joseph Shepard at the time, asked to get a position there, and he said no. And so what he did was he just came back every day and kept asking until he got something. And then when he got that something, he made sure to do a really good job at it so that he would get invited back for more.
Exactly.
So
That's it.
Yeah.
There's a question.
I had a question. So let's say like if any of us are committing to a school that doesn't explicitly have like aerospace. So like I personally am going to Chico State and like we have mechanical and mechatronics, they don't have like things like aerodynamics or like, like flight related stuff. What's a good resource? Like what would you recommend doing to kind of like learn some of this like stuff?
So mechanical and aerospace engineering are almost the same thing. You're gonna learn a lot about what aerospace engineers learn. It just won't be applied to flight. You're still gonna learn like fluids. I still learned statics. I still learned how gears worked, even though I hated that. So you're gonna learn everything. And mechanical and aerospace are usually pretty tied to each other. So you're gonna be fine in mechanical. And if you ever wanted to go to grad school, mechanical undergrad is like, you're gonna have no problem going into like an aerospace master's or PhD if that's what you wanted. But if you did want to learn, there's a textbook from Anderson in aerospace. You just Google Anderson aerospace textbook, like that's the one everyone uses. But there's also just like a lot of online lectures that you can look at. But I actually just wouldn't worry about it too much because the mechanical and aerospace fields are really, really combined. So, but if you're really curious about learning about, well, how does an airplane work, or what about engines, rockets, efficiency, stuff like that, then, online lectures will be fine, but you'll get it all in grad school if you decide to go there as well. Yeah.
Okay. Well, thank you so much.
Yeah. Thank you.
Where's the pizza? Come on in.
Yeah, no, I'm good.